visualization and machine learning. So as far as data visualization is concerned, we looked just before just before the break about different visualization types and thinking when is the visualization suited, and when should you use, think about when you should use points or lines, what color you should use to show contrast. Green and red shows a good contrast, but light and dark blue shows quite a soft contrast. Whether it's worth including straight lines or curves of best fit along your plots, or if you need to do something that's got an overlay as well. There are some great examples online of data visualizations and interactive things, but we'll cover loads of those in the module on data visualization. There's a great book written by someone who's not actually an academic, but an expert in data storytelling, called Andy Kind, and his book is sort of the core text that we'll be using for that module. So for machine learning, we've got to remember what the public thinks of machines and AI and ML as a whole. So they're what we call black boxes, in that you get data into an AI algorithm, it does some wizardry as far as lots of the public who aren't experts in AI are concerned, and then it churns out an answer. So what is it doing in that bit in there? And visualization helps us convey some understanding of what it's doing, which lends confidence to the results. Okay? When I was working in the healthcare domain, naturally people were quite concerned, especially the doctors. Some of them were completely sold by AI and really happy with it, and others thought that it was never going to be as good as a doctor, couldn't give advanced warning, couldn't be reliable, and I couldn't tell them how it worked, therefore they couldn't trust it. Whereas they trusted their stethoscope, they trusted their measurements, they trusted their ECG or heart rate monitors and things, because they'd gotten used to them. So the biggest thing was, one, showing it over a long time. So taking example patients and saying, look, let's churn this patient's data through. You can see what's happening there. Here's what the AI is saying what's happening. And putting your story as a doctor next to the AI algorithm, that helps. So there's some data storytelling going on there. But a lot of that's down to the visualization. So giving back control over what the data is doing and the AI is doing. So that's really important. But more generally, just showing which algorithms work better. Some machine learning algorithms are suited to some problems better than others. It depends entirely on what the data looks like as a structure. So you can plot with different strategies according to different performance measures. Does it matter if your algorithm's not 100% accurate for close by, if it's close enough, or does it have to be really accurate? And that's really important to convey in the plots. Okay. How many dimensions or features are inherent in the data? How many of those do you have to represent? If you have to represent lots and lots, then you need to think of a really special way of visualizing that data. Okay. How much data should I use to train a machine learning algorithm? That's one of the first times we talked about training here. But in essence, machine learning algorithms, as I said, they're a black box generally. They start with almost no knowledge. You train it and teach it how to solve a problem based upon some data, and then you can test it to see how well it solves that problem on new data. i.e., does it generalize? Has it actually learnt, or is it still just stupid? Okay, so we'll be covering more about that later on. So we've gone over some of the basics of choosing things like axes, normalizing data, and determining the type of plot that you want. Is there a more general set of principles for choosing and composing different features to pick a particular visualization? Well, yes. There's a few different approaches. One of the more basic ones, but that's really suitable here, is called the grammar of graphics. So it divides plots into layers with different aspects. So the aesthetics or the geometry, so the shapes and things, the statistical aspects, so the scales there, and any position adjustments and movements. Then you've got scales, coordinate systems, and groups or facets. So if you look at a histogram, for instance, or a bar chart, you'll have different bins or the groups for that. And the geometric element is the bar. Okay. In terms of trends, can we automate the process of choosing the right visualization? So there are commercial products like Tableau you may have heard of. We're going to be working with Click at the end in the data visualization module this year, so you'll be trying out that. But if you can use Click, you can pick up Tableau generally, although there's some, you can get free access to the program and do some digital certifications in Tableau as a student for free, I believe. You can definitely download free software from them. So, but recent work suggests there may be a path towards at least a recommendation system for visualization based on data properties and general rules of thumb. Now, you could do simple visualization, or we can take it more advanced. We're not going to worry too much about how we create advanced visualizations, but thinking about how you want to represent that's just good to get you exposure to some of these aspects. Okay, so when we've got scatter plots, for instance, that are relatively simple to start with, you can use a library in Python called Seaborn to do the plotting of those. But start off with a scatter plot, quite easily add a trend line. But it doesn't just add a trend line here or a line of best fit for the orange and the blue points, and they overlap almost perfectly. But you've got a shaded region as well for that confidence of the line is there, we're pretty sure, but it could be up or down slightly, and that's what the shaded regions of orange and blue mean. So it's all of a sudden giving more information to you straight away. Maybe you've got different variables and you need to try and compare and contrast them in different ways. So having multiple different visualizations or different views almost of the same thing. Imagine if your data set were more like a cube and had different things, drawn on the surfaces of that cube. Every time you turn it a different way, you're going to get a different bit of understanding of what's going on with that data. And visualizing data is much the same. Okay. You could do pairwise comparisons of different variables. So if we have this data set here, which is to do with tips, and we'll look at this in more detail in Colab shortly. So if the total, based on the total bill, how much did the group tip, how big was the group, and what percentage was the tip, or what proportion was the tip. So each of these things is then drawn along this grid horizontally and vertically. Right, so here we're plotting total bill against total bill. So that's just the distributions of the bills. Here we're plotting total bill, so as the bill increases, we're plotting it against tip. So as the bill increases, the tip generally increases. We've got generally a diagonal line going on there, but it's not perfect. So you're not guaranteed that for a big bill, you're going to get a big tip. Okay, but it's more likely than for a small bill. Total bill versus size. The more people in the group, so when it's just one person, it's quite small. 2, it ranges. 3 tends to be a bit higher. 4 tends to be a bit higher. And we've got less data for 5 and 6 people because there's less tables of 5 and 6, far more tables of 3, 2, or 4. What about the percent? Well, it looks like there's a negative correlation or a negative line going on here. So a line going diagonally towards the left. So that as the total bill increases, the percentage of that bill that's given as a tip tends to slightly decrease. Not by much. So hopefully you can see how these things compare and what kind of information that you can get from a pairwise comparison here when you've got 4 variables that you can't just plot on a single visualization very easily. You can use other measures, say heat maps, for instance. Say the brighter the color, the higher the number. So if you wanted to, or the number of events of that happening. So if we took total bill and grouped those so that it was in different boundaries, so or bins. So total bill between $3 and $8, $8 and $13. Well, that tends to be a couple of people. 13 to 18. That's quite likely to be a couple of people. That's observed quite a lot there. But we've got some lighter purple areas as well. So we're also seeing a bill between $13 and $18 for 3 people in quite a few cases. Or maybe you need to do a box and whisker plot. So depending on what the time is, what was the total bill? If we look at this box and whisker plot, it's quite clear that lunchtime bills are on average, so the center line is lower than in dinner time. And the upper quartiles and ranges as well are well inside, sorry, for lunch, what they are for dinner. So on average, dinner is more expensive, but it could be cheaper. So let's close the PowerPoint, and we've got the Colab notebook on information visualization. Now for this one, there's also a file in the link that I gave for today's notebooks and things called ceosdata.csv. It's very similar to the CEO's data that we got from Wikipedia, but it's been formatted. We've gone through some of that process already rather than having to do it all again. Okay, so feel free to yes, Innocent, tell you what, I'll just take a second and share that link again. So that's got the files in. So if you download that, you'll have the Colab file and the data set that I'm talking about, as well as the slides for today. If you want to go straight to the Colab page though, just to look through the code, then it's there, but you will need the data set from them. Okay, so this isn't an extensive notebook in any way, and it's just based on the data that we've just been looking at in that presentation. Hopefully this isn't nearly as scary as the data wrangling one is, and you actually start to be able to spot some standard stuff or understand maybe from the code and the comments what it's trying to do. Obviously, I'm not expecting anyone to be able to recreate this or write this from scratch or even necessarily edit it and make it work straight away. Okay, but just exposure is good. Just spending time with it and seeing what's going on there. So first of all, I'm telling it to just make sure it's installed all the relevant libraries and things that we're going to need. And we'll do some imports as well, make sure they're loaded in and ready. So we're going to bring in the CEO's data, CSV, and just do a bit of cleaning. So any of the CEOs that have in the column of the table that says when there are CEOs since this date, it's just making sure that it's got rid of any boxes because some of them had square brackets in. So we're just removing those. Okay. So now we've got the data, we're going to split it into two different data frames, one for founders and one for people who are just regular CEOs. Okay, so we'll just split the two of them, and then we'll be able to plot some graphs once we've got them separated out to see what's going on there. So for information, who are the non-founders? So that's a bit of information about the data that's in that table and who are the founders. So these will be all the founders of these different companies here. Okay. So we've got 11 founders there. And if we just drop the .info, let's just rerun this and see what the regular CEOs look like. Okay. Zoom video communications is worth an awful lot more money now than it was then. So we're going to plot some graphs and get to understand this data set and see what's going on. So we've got the founders data frame here. and we're going to plot so founders dot plot, so tell it to plot information from the founders data table. We're going to do a bar chart. Our x-axis along the bottom is going to be what the company is, and the y-axis is going to be the since year, so when was the company founded. Okay. And we're also going to print out the information. And this has created that really bad plot that I told you about earlier on in the slides, where it's just plotted on a scale from 0 to 2000. And part of the reason for this is the date-time formatting of those numbers. So it's measuring from that. So what we need to do is just swap them around and set that scale them by year, and then rerun it, but limited between 0 and 70. This would be a bar chart rather than a histogram. A histogram's a specific type of chart based on the number of occurrences in a certain band, or bin we would call it, whereas this is just plotting the number of years for that company. So we haven't grouped the companies in any way. But a histogram is just a special type of bar chart, yeah. So if you're getting type errors, chances are either you haven't imported this, like brought in the CEO's data.csv. So if you need to, you just have to hit this files bit at the side, Shamal, hit the up arrow here, and then it'll let you upload that file, CEO's data.csv, and then that will then be imported. If you're still getting type errors and you've got that in, then cheaty way is to just click on the box where you are, click run time and run before, and that'll run everything before the current block of code you're on. So it's almost like just, oh right, start again, and then continue. So let's do a comparison though. So let's get the current plot and the information. Yeah, great. So we can see for founding CEOs and other CEOs, we've got a line plot here. I'm just going to zoom right in so you can see. So this is all fine and well, but it's not overly clear, is it? It doesn't give us our information. So instead of doing a line plot, we want to group them by when they were founded since, and then plot them as a point rather than as a curve. So the founding CEOs as blue points, and the red ones, we're going to leave the line join them up, but we've got the points shown as well. Okay. So what if we need to think about scale? We're just redoing some of the experiments from the presentation slides now. So if we've got this chart here, and it's really simple in Python to plot some data. So if you know what the data is and you've not got too much of it, you can just enter it like this. So a graph data frame or a table, and we're just going to create this new table. It's a PD or pandas data frame or table, and you set it up with this structure. If you wanted to do something similar to create your own data frame or table, just change around these numbers and what these titles are, because that will be the X and the Y axis. So scale 100, value 800. That'll be the one here. The next one is scale 200, value 1200. This one here. And then we've got scale 500, value 2400. So that's this one here. And then you just tell it to plot, where the kind of plot you want is a bar chart. X axis is going to be scale and Y is value. Okay. If you wanted to swap those around, you absolutely could do. X as value and Y as scale. And it still is disingenuous here, because it looks like it's going from 800 to 1200. The same gap between those two is the same as the gap between those two, but it's gone from 1200 to 2400. Okay. But when we plot it as a line chart, it's still the same. Okay. So hopefully everyone's feeling more comfortable seeing that you don't need too much code actually to create a visualization, and it looks exactly the same as what we've got in those lecture notes. So we're back to that normalization activity where we had two different sets of data. We have a baseline and alternative for 3 different companies and different values for those, where they weren't normalized. If we want to normalize them though, all we do is get that value R of alternative and divide it by the baseline. Okay. It looks like a complicated line of code, but that's all it's doing, I promise you. It's just going along and dividing the alternative value here by the baseline. And then when we run that, we end up with our normalized prediction performance. So from the blues all being 1, how much better is the alternative measure? Okay. Now, I'd recommend for anyone who's not overly confident, when you're doing the hack as a group, getting things in the data frame format, which I'll show you how to do with the data set they'll be working with, and then just doing df.plot and choosing different kinds of plots for different things. Whether it's a line, whether it's a scatter plot or markers, let's say circles, as the examples above have given. So you've got a line plot and you've got markers on them as well. So I'd recommend doing plots like that. If you have more of a programming or computing background and you're more happy to try and go ahead and try something different, then you can use Seaborn, which requires a few more lines of code, but it gives you slightly better looking plots. But naturally, I'm not going to penalize people too much based upon the quality of the plots. It's the story that you tell with them. So if we take some simple data that we create, then you can do a Seaborn plot. And it's that simple. You just give it the sample data frame, which we create in the code block above. Okay. You can also fit the lines or the regression lines or lines of best fit quite easily by just saying fit underscore reg equals true. You don't need to do any work with that. The code will do that for you. So here we're going to load in that tips data set that was mentioned before. And you can see there is some more information in this than was displayed in that previous set of visualizations. We focused just on 4 variables or 4 features, whereas there's far more here. We've got what the actual value of the tip was, the gender, whether or not they were a smoker, what the day was. Okay. So there's information, plenty of information in there. If we load that in, and then we can start to do some plots. So if it's lunchtime, if it's a Thursday or a Friday, what's the amount of tip percent of the total bill? So are people more likely to tip, or more money or a high percentage of the bill on a Thursday or a Friday? It's not overly clear. Likewise for Saturday, Sundays, and dinner time. So all of these things are just giving slightly different complementary views of what's going on with the data set. So it's best to supplement with lots of different plots as you go. And here it's done one of those comparison plots between total bill, tip, and the tip percentage. Okay. Now it's broken down by size of party, but in essence we see overall, more often than not, we're seeing a party of 2, and the tip percent is generally peaked around just less than 20%, somewhere between 15 and 20%, which is slightly low for an American tipping policy, but it's not outside the realms of possibility. Okay. I'm just going to set the rest of these running, and we'll get the heat plot and the box plot and the total values. Okay, so we can see all these different views of the data set and take some of these away and think about how you might use those with some of the data that I'm going to give you tomorrow. Okay, does anyone have any questions about data visualization? It's worth highlighting that exploratory data analysis isn't just data visualization, but data visualization is a big part of it. It's normally supplemented with statistical analysis, so getting some measures like the mean, the median, the variance, different groupings, some sort of clustering or other machine learning basic models, but in essence it's a very quick look into what's going on in the data. Okay. But it doesn't seem like we've got any questions there, so the next thing that we have to do is going to be based on borrowed from tomorrow. Essentially, we're moving quite quickly through this stuff. So I'm going to give you another link for tomorrow's activities that we're going to do the first one from, which is where we're going to begin our work on machine learning. Okay. So I'll do that just shortly, but I think before then we'll take a 5-minute break, just because I've been talking quite a lot for everyone. So have 5 minutes. If you've got any questions, please feel free to throw them up in the chat, and then we'll start on the machine learning aspects. Yes, sir. Yes, you are supposed to understand the graph to be able to interpret it in essence, especially if you're the ones creating a graph. But don't worry if you don't understand some of these ones that I've just thrown up, because I've not explained the data set brilliantly. You've not had a lot of time working with that. So the data interpretation is not an easy thing with complex visualizations and complex data sets. So it takes time to get good at that, and that's why we spend a whole module on data visualization. I would hope that we'd be able to upskill you, Mohammed Yunus, in being able to understand graphs, read them, getting more used to them. And I would argue that you're going to need to get better, whatever job you're working in, you're going to need to get better at reading graphs as time goes on. So I think it's good for you to try and confront that, but acknowledge that that's where you think you've got a weakness. So spend more time getting used to it. Okay, so we'll take a 5-minute break and back at 14:20. And I'll share the link for the files that we're going to be working through this afternoon. Hi everyone. I was just checking out that recommendation you made there, Alice. That's a really good one, Tufte. Yeah, it is a classic text. Absolutely.
It's really, really pretty.
Yeah. I'm going to see if I can find mine now. Okay. The one that we end up using is Andy Kirk's data visualization, but it breaks down absolutely every type of chart, explains the editorial thinking behind them, a whole range of different approaches, some that I'd not heard of by the time I picked up the book last year, so that was really exciting as well. Plus a load of online resources that he gives, but it's just whatever helps you in getting more comfortable with data visualizations, then throw yourself into that really. And this is part of what I love about this course, and the conversion nature, the peer support, and also the different experiences and backgrounds that everyone has means that you can all learn a lot from each other as well as from your academic team, rather than just being all relatively similar backgrounds and going on the same journey. So any recommendations that anyone else has along the way, please feel free to chip those in. So we're going to go on to the last session for today and talk about supervised machine learning. By supervised, I mean that there's data and there's clear outcomes for the data that we're looking to see. So if you wanted to look at spending profiles and compare them for men and women, for instance, female, male, then you might look at the amount that they spend and try and predict based on what they'd spent if it was a man or a woman that had spent that amount of money, so that you could then target marketing or do some other further analysis from that. So the supervised nature is the fact that you've got the labels or the information about whether or not they're male or female. So this session does come after a previous session in the IBM Open Data Science for All course called on decision trees, but decision trees are a bit complex. I'll show you a simple example of a decision tree tomorrow, so I don't want to spoil that, but here we'll just go through the basics of supervised learning from regression and classification. So regression as a task and as a building block, really. There are two general cases that we'll consider to solve the regression problem for a continuous output. So linear regression, and it sounds simple, linear, and most of AI ends up working with non-linear functions, but actually you can do quite a lot with linear functions. You could do really quite well in lots of cases with linear regression. Okay, so it should never be looked down on, despite the fact that it doesn't ever hit the news like deep learning does. Okay, so linear regression is about fitting a linear or a straight line function to optimally match data between classes. If we've got a classification problem, for instance, we're doing what we call logistic regression. You may have heard of that if you come from a psychology or sociology background. So that's generalizing the techniques to classification. So there is an element of non-linearity in there. Okay. The slides have some maths on. Please don't panic if you're not uncomfortable with it or not familiar. Don't worry about it, because we're going to get on to the plots and the understanding what it's actually doing, and then seeing some of the code, not the maths. Okay, but it's linear because it's a collection of added terms added together. So this beta 0 plus the beta 1 x1 plus beta 2 x2. So it's just this plus this plus this plus this, and that makes it all linear. Okay, if it wasn't all just added together, it would be non-linear. There would be some other things, some multiplications and some other factors going on there. So what we're trying to minimize is the difference between the true outcomes in our data and what our model predicts those outcomes should be for some data. We do that by trying to minimize the mean square error or root mean square error. Okay, and instead of going through the maths and things, I'm going to show it graphically what the mean square error is. So the mean square error is just the sum or the added up differences between each data point and the line. So you go from the data point down to the line or up to the line, and you add those up. And if by moving the line slightly, angled slightly, or completely up or down, that you could improve or reduce the overall added up distances from every point to this line, then there's a better curve and you would do that. But this line here is the optimal or the best one for this data, this red curve, for the blue data points. So you could not reduce the added up, the overall distance between every point and the line if you moved that line up or down or angled it slightly differently. That is the perfect or the optimal placement of that. And the nice thing with linear regression as a simple standard technique in AI machine learning is that you're guaranteed to always find the best line just from the maths of it. It's really simple and guaranteed. Very little in AI is guaranteed. I think Yasmin may be able to attest to the, as soon as you got involved in the deep learning module, the amount of training and variability and underfitting and overfitting and complexities with models that you need to think about. Whereas with linear regression, you tell the computer to do it, it does it, and it's done. So it's nice and simple, but it's not overly complex. So if the data bent up slightly, it wouldn't be able to cope with that. Okay, so things to be aware of. So it's worth doing some plots and some understanding first of all. So looking at the correlation or the different relationships in the data, you want to make sure that there's a nice positive or a negative, just a straight line correlation, we call it, but grouping of data. If it's scattered all around or flat or vertical, linear regression isn't going to be suitable. It's best suited when your data follows a nice straight line. If it does follow a nice straight line, then it's definitely not worth using any complex AI either. Just use linear regression. Okay. Now, it is susceptible to what we call overfitting. So it gets more confident than it should be about how well it's fitting the data. But you can fight against that slightly. And the way that you fight against that is by being clever about which features you use in your data. So have a look at the data, clean it, and then think based on understanding of the application domain and of the data, whether or not you're using the right features. So what you can do if you don't have any prior knowledge of the application domain is use what we call lasso regression. And this naturally looks at the whole range of features in your data set and then starts to ignore some of them and sees whether that straight line that it had drawn could be better placed if you ignored certain features in your data set. So if you collected a whole host of things and tried to measure in my secondary school, we did a simple statistical test based on people's height. Could you predict what their foot size was, or group them at least? Is there any correlation between height and foot size? So if you collected the data for height and for foot size and for parents' height, parents' foot size, and scores in a maths test, scores in a maths test isn't going to be relevant at all to someone's foot size. So lasso regression, instead of trying to use that information, as the machine learning goes, it will just ignore it. Okay? So it's really good by using what we call a penalty term. Ridge regression, instead of trying to just completely ignore it, just says, okay, I'll take that piece of data, but I'm not going to listen to it very much. I'll just turn the volume down on it rather than mute it completely. Okay? Ridge regression is quicker to fit than lasso. Okay. We're going to jump past some of this because of the nature of the complexity and the time that we've got for this week. But linear regression is going to be important for you in the hacker modeling some of the data aspects. So that's for regression. So if you've got some data and you're trying to plot correlations or understand what's going on with that, and continuous data. What if you're doing what we call classifications? So taking some data and then classifying from it. So based on bank transactions, is this fraud or not fraud? Okay. Is this company going to be successful or not? Based on an email chain, based on the contents of an email, sorry, is this spam or not spam? And original spam filters looked a bit like this, they were logistic regressions. And the way that they work is you have a scoring system along the x-axis, and then this curve called a logistic curve, like this red one here, was a standard logistic curve. And based on whatever the score was, if it's greater than 0, then this logistic curve would say it's got a high probability, it's got a greater than 0.5 probability, therefore it's likely spam. But if your spam scoring system said it was lower, then it would say no, it's not spam, and it wouldn't put it in it would put it in your inbox. So logistic regression is about that classification thing. Does it go into the inbox, yes or no? Just a simple binary or 1-0 decision. Now, unlike linear regression, logistic regression needs to do a bit of training. So it takes a bit of time after seeing the data, getting used to it, understanding it to see whether or not it can generalize. But then it does work quite reliably. Okay. So we're going to go and use a simple data set called the wine data set in the Colab notebook, and use logistic regression on that to try and see, based upon some of the information, whether or not we can predict an outcome for that. Okay. So if we jump over to Colab, on the notebook that's inside that set of files that I shared the link for just now, there's also the link just to the Colab file there. Okay, so we can jump straight on and start to run through this. So as ever, first of all, we just install and import things ready into the, let's just clear them out. Okay, so we're going to bring in the wine data set. And the wine data set is a data set of wine information. So I believe it's based on Australian wine, but the level of alcohol, different acids, ash concentration, magnesium concentration, all of these things. Okay. And we're going to turn that into a data frame or a table so that we can look at it then. Nice and simple, but you can get a view of what's going on there. Okay. So there are 3 types of wine here. I believe that they are white, rosé, and red, off the top of my head, but I may have the order wrong slightly on that. But in essence, we're going to try and say, well, based on the information in this data set, so for each row, bottle of wine 0 has 14.23% alcohol, 1.71% malic acid, 2.43% ash. It's going to take all of this data in and try and predict whether it thinks that this is a white, a rosé, or a red. So white, rosé, red. Okay. Now, if we used all of the data in one go, we wouldn't be able to test it to see if it's actually generalizing or doing well outside of that. We'd just be able to say, you're great at doing what you do. In the same way, the easiest way to contrast this to the real world is to say, okay, if I had a table tennis table and folded up half of it and constantly played against myself, and I'd gotten great playing against myself, that's my training. But if I don't ever go and play against someone else and test myself, I'll never actually know if I'm any good or if I'm just good at playing against myself. Okay? So that's the difference between training and testing. So it's done the split, and we're going to see how well it performs. So oddly enough, for some reason, the code seems to have disappeared for testing out on the wine data set. I'm just going to scroll down just in case we move down. Here we go. So yeah, it's been moved here. So we can apply this onto our data, and it seems that we've been 100% accurate. So based upon our data set, our logistic regression model is 100% perfect at predicting whether or not a bottle of wine, based on the data in here, is white, rosé, or red. So therefore, you don't need a person to label them or to look at them. You can just take this information and automatically predict that 100% of the time based upon our test data. And it took less than a second to test and to implement. It's worth noting that with the whole talk of Brexit, in the UK, naturally, if you're familiar with Brexit and the situation there was a lot of talk of whether or not technology would be able to solve some of our problems at the borders. And depending on the amount of data and the information that you have, some problems can be technologically overcome quite quickly. And this would be an example of one of those where you don't need to have a human go and open crates of wine to see whether or not it's white, red, or rosé. You can take some measurements. Some measurements require opening the bottle, but some of these measurements may not require opening the bottle to be able to understand, and you may be able to just declare them. And therefore, a logistic regression model would be able to accurately predict whether or not what type of wine it was. Okay. For linear regression, we've got an example here where we've just got some random data that looks like it follows a nice straight line. So if we just plot a linear regression line on there, and it's recreated perfectly, the one from the slides. So in general, it's very unlikely for a model to get 100% accuracy. Shaheed, good question. So it's possible, in theoretically, for some data sets. For lots of data sets, it's not possible, and it's very unlikely. So if it weren't such a simple problem with such a small amount of data in this data set, I would be questioning that. But the fact that it's only 178 rows with 13, which is quite a lot of columns for that small amount of data, I wouldn't be surprised if this could accurately predict wine, also because I know it's a simple data set. So it's always worth testing just to make sure. And sometimes we do it where you have a training data set. So you use 70% of the data for training, and then 15% for what we call testing, and another 15% for validating. So you almost test twice on two separate groups. Okay. So you've run it, excellent, Adu, and you've got an accuracy of 96.3%. That is very interesting. So let's rerun and see what happens here. So I'm just rerunning it over and over. Tell you what, I'll go from the start and reload the data set in just to make sure everything's working okay. And it's probably because there's a random element in logistic regression. So it's not like linear regression where it's always the perfect straight line and always works the same. It can vary from time to time when you run it. It's generally very reliable. Okay, so let's use logistic regression again. There we go, I've got 94.4% accuracy this time. So each time we run this, we're getting slightly different results. So what happens if you use a different train test split? That'll be where it is. So Innocent's got 96.3. So I'll come to your question in a second, Oluwasimi. So we've got 96.3 and 94.4, another 96.3. You see, based on the way that the data's been split, it may be that there's some unusual data points in the test set, not in the training data set, that it should have seen and would be useful to see and generalize better. Or maybe it's just found some point where it's trying to learn and it's just struggling to get that last bit. And this is the thing with complex AI models. I mean, this is logistic regression is quite a simple one, but it still has an element of randomness in there when it's learning how to do its job. If you scale that up to something like the deep learning models that Google use, for instance, or that Microsoft Teams uses for that fuzzy background of yours, they're not 100% accurate, but even if they were, if you ran it again, it might not be. So this is why we need to make sure with AI models that we do robust testing over and over with different variants of a data set to try and see what's going on. So it's not at all a surprise that we've got 96.3. Oh, Addy, it's getting even worse each time we look at it. So 88.9%. So yes, you could use a random seed. Addy, absolutely. So if you fix the level of randomness, then it would probably be fine. So it depends on what the project is you're doing, Amir, that you've said. For this, we're using 70% of the data to train and 30% to test. Okay. We'll rerun these two. That sounds like you've made a hypothesis there, Abdul. I would very much invite you to keep running the notebook and test that. So, very short notebook, because I don't want to get too bogged down in some of the machine learning aspects. But let's have is everyone comfortable with the idea of what logistic regression is for classification and what linear regression is? Yeah, sure, Shamar. So they do two different jobs. Linear regression is for continuous data that has, completely different scales and doesn't just go into discrete groups. Logistic regression is for classification, say discrete groups of things. So based upon what someone's job is, are they going to be rich or poor? Whereas the regression part may be based upon someone's job, what salary do you expect them to have? So what actual number, rather than just going rich, poor, or working class, middle class, upper class. Okay. So in terms of, so for my healthcare application, for instance, that I looked at before, regression would be what's the value of the heart rate for that child going to be in 10 minutes time? So the actual value. And I'd get nice straight curves or bendy curves or whatever they would be, but to do the prediction in 10 minutes time into the future. So all I'd do is extend this and then go, I think it's going to be up here. It might be up there or down there, but I can extend the line and say, on average, it's expected to be about there. Logistic regression would be, is this child going to have a cardiac arrest in 10 minutes time? Yes or no? So 1, 0, yes or no? Okay. Yes, they are, Shemaya. Yes, the regression line and the line of best fit, for the purposes of today, they are exactly the same thing. We'll break that assumption on the course, but for today, absolutely the same thing. You absolutely could, Mohammed Yunus. You could be deciding whether or not someone is a thief or not. So Yasmin and the other students on the MSc AI, as one of their modules for the ethical debate, had to discuss sentencing systems, actually automated sentencing systems and algorithms. And well, I don't know if you want to jump in here, Yasmin, about any particular points about that debate.
Oh, sorry. Yeah, the debate was more on the ethical side of things to see if an AI robot is trustworthy enough to become, well, to replace like a human lawyer or like a human judge. And it was really interesting that the class was split, half was like for and half was like against. And there is quite a lot of promising research out there, but it's very hard in terms of, yes, the algorithm might be accurate, but there's always a human element when you're dealing with things like court cases. So yeah, it's very, very tricky when you bring ethics into AI, because yes, AI can be like, it's really accurate and they do some really good stuff, but then when you have people's lives on hold, it can be damaging sometimes. And especially there's quite a lot of things with I'm not sure if you guys heard that there's like a lot of bias in tech, and some people are saying that the bias can leak through into algorithms, and then that in turn, especially if you're going to have algorithms in a law perspective, it could go one way for one type of person or one way for another type of person. So yeah, it's very, very very difficult when you bring ethics into it.
Yeah, thanks, Yasmin. So there's bias in terms of like loads of different sources of bias, but just quite clearly, we talked about one of them slightly yesterday in terms of the imbalance of the fact there's too many, as I said, people like me, white men in tech, deciding what's best for the world, and that creates a huge bias and a problem there. And then there's bias in the data that we use. So the standard thing in machine learning is to take some data and then generalize a machine or an AI system to perform that task, which works all fine and well until you consider that, for instance, on average, a white person in the USA gets a lower sentence for exactly the same crime as a black person in the USA. It's a statistical fact based upon the data, and it's a horrific fact. But the nature of that, if you use that data to then use automated sentencing systems, it's always going to perpetuate that and give a harsher sentence to someone of color. So we need to make sure that the errors in the data and bias in the data is accounted for, as well as the people making the decisions and using the systems. Oliver, in typical regression variables should be given for errors and autocorrelation. Is that applicable to AIs? So you wouldn't really want to give a variable for your error, otherwise your machine is trying to cheat itself, generally, from a statistics point of view. And then for autocorrelation, you can do, but really we're working with data that we're working with a slight correlation, but not an overwhelming aspect here. We don't want to get too bogged down in the statistics of that, but you could use lasso regression, if you're familiar with that, to try and get out of that problem, based on the fact you've brought up errors and autocorrelation there. I assume you understand some of the statistics background. So Mohammed Yunus, would you ever consider applying an ML logistics model based on the information given in the form and information presented online on different social media platforms? So this is a tricky one. There will reach a point where it will happen, Mohammed, in terms of whether or not an automatic decision-making process will be used in the same way that they're used to help sift for job candidates now. And that's a problem in lots of cases. But if I'm ever involved in the system that is created for it at BCU, then we'll make sure that it's as unbiased as possible. Especially as we have a mission at BCU for the West Midlands, for Birmingham, for people who are disadvantaged, and improving equality, diversity, and inclusivity. So we'd want to make sure that we gave opportunity rather than took that away. But if we were receiving 100 applications for every post available on a program, then that's a huge administrative burden, which then falls onto the academics generally. So I'm the one that has to look through every application when it hits my tray to assess personal statements and CVs and things, and to do the interviews. And when we started doing interviews at the beginning of the recruitment process, based on the popularity of the course, and after a certain cut-off point, we stopped doing interviews for everyone because of the time it took, and it stopped me from being able to teach properly or from doing my research, for instance. And the argument would be the same for an automatic decision-making rule, but there'd be probably a catch in the system to say anyone who is rejected gets a human check, just to make sure that there isn't anything that could be done. But maybe there's a way of doing it slightly better, whether or not it tells you when you're submitting your information online what the likelihood of you getting a position is and what areas you're weak in, and therefore you could improve yourself and make sure that your application is better, whether that's writing a better personal statement or going and doing a quick online AI course or something to upskill yourself and make sure you're showing that, yeah, maybe you didn't perform as well on your degree, but you've got work experience for years, making sure that comes across. Yeah, Alice, that is absolutely true. That did happen. And it's not the only place, Google is not the only place that's had something like that happen as well. Yeah, I thought it's a great idea for a project. As I said, so it's sort of linked to some of those learning analytic aspects that I've been talking about the last couple of days, of based on someone's entry criteria, and did they come up with A levels or GCSEs or college or BTECs and things, based on that coming into BCU as an undergraduate, how have they performed, so that we can then go, okay, if they've done A levels, chances are maybe they need more support doing module X, Y, and Z, and if they've done BTECs, they need more help with modules 1, 2, and 3, and we can just do it. But it's more about a supportive mechanism rather than a discriminative mechanism there. And that's where you need to get an ethical perspective on what's going on. Algorithms are very funny things, in a not funny way, in essence. So I often, whenever I'm talking about financial algorithms and things, for instance, so I applied for a credit card and went through one of their financial assessment checks, and so did my wife, who we both worked full time. She earned more than me, was actually in a professional job as a doctor, better stage, more secure job, and everything better on paper in every way, apart from the fact that she was a woman, which according to this algorithm was a worse thing, and she was 20% less likely to get granted a credit card than I was, just by virtue of being female. If you're talking about the job sifter, it's not overly difficult to implement, actually, if you get everyone to always submit their applications in the same format. So if you have an application form instead of asking people to submit their CVs, it's much easier. It's not impossible if they submit their CVs, but just from the form, you can look at the type of places people have worked, how long they've worked at those places, if it ranks those places as important or not important, what their college, graduation scores was, what their A level and GCSE or other grades were going into the job application round, and then it would give them a score, and then it would just rank and say, yes, we want to hire you, no, we don't hire you, based upon all the people they have recruited already. So it doesn't take an overly complex thing, especially if you've got as much time as Google, money as Google, and the team can just get on and do what they want at Google in a lot of cases. Alice, did you want to jump in there?
Oh yeah, I was just doing some work on this recently with our graduate stats from my job, and one of the difficulties that we have with it is the way that grade percentages have changed through the years. So last year, 32% of people got a first. The year before that was 28. When I graduated in 2004, it was 11. So you have to look at how things change through the years, and then I think you score much more highly on engineering and math subjects where it's possible to get higher results than on humanities subjects where it's not physically possible to get 100% because you can't prove it. And yeah, it does get really, really annoying and complicated. But it was really interesting and part of why I ended up on this course.
That's great to hear. Thanks. Absolutely. And yeah, I completely agree. That has been a bit of qualification inflation, we call it, in the industry, and lots of people acknowledge it's a problem. Not many people are doing anything about it, unfortunately. My argument, I often back against the whole the maths engineering versus humanities argument, but it's mostly backing back against the academics and the teachers in the humanities and social sciences, because the maths engineering, yes, it is technically possible to score those marks and get 100%, but often the comparison falls apart either because the maths ones aren't testing hard enough or pushing hard enough, or the ones in the humanities aren't using the whole grade scale and aren't being fair then comparatively. But it's unfortunately, academics, we're stubborn, we're grumpy, and we do things how we want them, no matter what the problem is, until someone makes it our job to try and fix.
It gets even more complicated once you start bringing in different education systems and degrees from around the world. The whole thing's a nightmare, but it shows how simple it is to look at a simple set of data that you could just rank, and that's far too simple for how complex the information behind it is.
So the neat thing is, it doesn't, although it looks simple, as in it's just chucking out a number. If I print out, let's just run it again. So let me just be clear about what it's doing. Each of these numbers, these coefficients, it's calling them, is a score and how much significance it's giving to each of the different columns in this data set. So that will be a different parameter for each column. So there'll be 1, 2, 3, 4, 12, 13 of those. So 13 parameters to see whether or not it's white wine, 13 to say if it's rosé wine, and 13 to say whether it's red wine. Plus another parameter each of those for good measure. So that's quite simple as far as a complex model goes, but it's flexible enough to fit this model. Our brains naturally use millions and millions of neurons, but you can use deep learning models with millions and millions of parameters if you've got enough data to reliably train it. And if a human can subjectively discriminate and do a task and be able to explain the rationale, the logic in that, then an AI system with the right data can learn that theoretically. It's how it's done practically and accounting for bias in the data and in the system. But it's all about, it could theoretically be done in the right conditions. It's just, we've got to make sure in AI and in machine learning that we try and affect those right conditions.
Oh, yes, exactly. I was just pointing out how it's one of the reasons I think that if people have come from not a computing background, it shows, same as with the wine, that an understanding of the information behind the numbers is really, really important.
Yeah. And I think that my one criteria, I mean, the university instilled this criteria for a conversion course for AI, that the entry criteria was a 2-2 and some of the things that are listed on the website. Actually, my criteria was slightly different when I started looking at this. I said that everyone who came onto the course had to be motivated, and that's why you're all here at this stage, and why some of you are getting offers, and that's moving on to that next stage and going to be starting in September, because I'm willing to take a punt on you and believe that you're motivated enough to be able to perform and to be able to, you know, succeed on this course in a career in AI and in life. And I think it's you're absolutely 100% worth investing in. Yeah, the choice. Yeah, it sounds a bit of a prophecy almost like that, doesn't it? But no, that was my main condition, and that's very hard to measure. And I can't subjectively discriminate and say whether or not someone is motivated 100%. But that's why we do things like this, the personal statement, the interview, and why the personal statement to me is more important than your CV, your academic background, all that other stuff. It's you convincing me that you're motivated enough and going to keep up with the challenging work and break through the water. So I think we've reached the end of today's session that I wanted to cover. So what we're going to do tomorrow, we're going to spend a little bit of time looking in slightly more detail at some other machine learning tools, techniques. So get onto a bit more classification from a few different approaches, just so that you can learn some buzzwords and see how different algorithms might work. And then we're going to jump from that into an explanation of the hack data set and the groups and how it's all going to work. And what we'll do then is put you all into groups, set you running. Myself, Yasmin and Mohammed will be joining us tomorrow as well, and we'll just be dropping in the afternoon a bit tomorrow and over Thursday periodically, although people can always, you know, can always email and ask us to drop into your group, and we'll yeah, jump in, see if you've got any issues that you want us to go through. But other than that, you'll be left to work on that as a small group, put together a few slides on something interesting that you've explored and understood from the data, using some of the visualization aspect and some of the machine learning aspects, more likely the regression things than the logistic regression or classification aspects. But yeah, we're looking to see some interesting, exciting things, or whatever excites you about this data sets. Okay, so thanks everyone for attending today. As ever, if you've got any questions, I think you've all got my email address now. I've shared it enough times, but if you want it again, just let me know, and email me with a subject line question in. Okay, thanks very much for attending. I'll close off the recording there and the meeting, and then I'll upload the recording onto the YouTube channel. I'll send out another link to the YouTube channel just in case anyone wants to re-watch anything from today again. Great, glad to hear that, Shemaya. Excellent. So, Abdul, what are good places in Birmingham to visit? It's quite a personal thing. I tell you what, I'll stop the recording first, because I don't think we need to record my sightseeing habits in Birmingham.